Welcome to Finite Element Methods. I'll be covering trusses today, which are used in a lot of applications. Now, the fundamental of finite elements is not based on how we model trusses, but trusses can give us a good idea on how to approach the general, uh, the general methodology for using finite elements. And it's the same basic idea, but in reality, the basis of finite elements is approximation of governing equations that tend to be differential equations or partial differential equations. While I have not covered those concepts yet, the trusses and springs that I covered on last time and what I plan to cover today provide the basis of kind of understanding the bigger picture perspective. And so when I go deeper into each of these subjects, things will become more apparent. And so, with that said, um, I plan to I plan to cover chapter 6 of my book, which goes into truss elements, and it has a more advanced theory, which is called plane frame elements. Basically, these are beams; they're interconnected, and it also shows how to do it in MATLAB, and it basically shows you the procedure and how to do it there, so that you can actually maybe even code this up. In this course, however, when I do some demonstrations in class, I'll be doing them in Mathematica. But it's okay to use MATLAB, and the book was written so that you can use it along with MATLAB. The coding it can make things a little bit easier. In general, what are trusses? Trusses are composed of slender members that join together at their ends by welding, riveted connections, or large bolts and pins. That's typically what you will see. Um, and these connections can be actually simplified. A lot of times, what we do is we say that at these connections, there's a very limited amount of bending moment getting transferred. That's the approach that's typically used when you're covering um, when we're covering these connections. Ideal truss members are connected only at their ends by frictionless pins and only loaded at the pins. No moments are transmitted at these locations. The weight typically of these members is neglected. Now, there's ways that people have to consider them. Um, we won't cover it, but it can be done. You can actually consider the, the the weight of these members. So, as a consequence, since moments cannot be transmitted, and the trusses cannot transmit these moments, we typically consider these trusses as two force members. And a two force member is a member in which the load only acts axially within the member. That's how that works. The trusses therefore become a two force member, and what that is that the member can be loaded only at their extremities by equal and opposite collinear forces. Here you can see a compression load, here you can see a tension load, and here you see a tension load. Well, they're all connected by a connecting pin. Now, like I said before, these connections can be more like a gusset plate or more of a welded connection, but listen to me carefully, we are making a modeling simplification, an idealization. Just imagine if I were to build a structural finite element model that tried to model every single little bolt and every single little detail of every single connection. That would be computationally very expensive. Imagine if I want to model an aircraft and the aircraft has hundreds of bolts and rivets and everything like that. Imagine if I model every single rivet and every single bolt in a aircraft application. That'll be very impractical. But instead, what we do, we try to understand the forces, the load paths, and then combine that with some hand calculations. So we want to be smart about that. So what we've done is a modeling simplification in which we've taken these connections and simplify them to a pin. Yes, it's not a pin, but once you know the loads in this area, you can then perhaps do a more local model of this area to understand how these connections work, or you can do a hand calculation as well. So say I predict that this pin loads up this force member, loads up 4,000 pounds going up. Well, I can go here and say, okay, 4,000 pounds going up. Okay, well, then 4 bolts have to take the 4,000 pounds. Therefore, each bolt has to take 1,000 pounds because I have 4 bolts. And then you can start making some modeling hand calculations to then increase your knowledge about these joints. So that's why these modeling simplifications are done, is because it will be computationally just intractable. You know, imagine I have to model a whole building with bolts and rivets and everything like that. Then that could be a major source of concern. So what is a finite element strategy for trusses? The first step is to idealize each truss member as a bar element and connect them through to each other through nodes. That's really what we want to do. So yeah, so we're going to treat each truss member as a bar element. In the previous lecture, we discussed how I could take a bar element and try to develop the element stiffness matrix for a single bar element. In step number 2, we describe the behavior of each bar element. And we do that by deriving its stiffness matrix and load vector in the local and global coordinate system. So we want to basically formulate the local element matrix equations for a bar element. I apologize. And for step number 3, I want to assemble the global stiffness matrix. Once I know the local element behavior for every single one of them, I can now assemble everything together. And I can assemble a load vector together. And once I have that, I apply the boundary conditions and solve the system of algebraic equations. You'll see later on, as we go to more advanced theories, that can turn any problem, any governing equation, partial differential equation, and can turn it into a system of algebraic equations. And that's an exciting point because you used to solve differential equations and partial differential equations, and you found the exact solution. Sometimes had exponents, it's sine functions, sinh functions, cosine functions, hyperbolic sines and cosines functions. Very complicated solutions. But what we're saying is that this course is going to teach you how finite elements goes about it, which is to discretize the domain in a way that what you end up with is a system of algebraic equations. And for linear system of equations, for linear systems, you will get a linear system of equations, which is easily solvable in MATLAB or Mathematica or even by hand, which I don't want anybody really to do that by hand. Now, in the book, I cover how to do that in MATLAB, how to take and solve different equations in MATLAB. And I'll show a little bit about that in the book. In case you're not able to get it, I'll show you some of the things there so you can kind of see what we're talking about. Discretizing the truss system. That's the first step. Given a truss system, here I have, and it's a very busy picture, so I apologize, but let's look at what we have. We have a truss system here. And this truss system has 1, 2, 3, 4, 5, 6, 7 trusses right here. So the first step is to discretize the system. And I know there's 7 trusses. Okay, fine. So I'll number them 1, 2, 3, 4, 5, 6, 7. And I know that each node, and you tell me if that makes sense, do you agree that every single point here can move up or to the right? So it can deflect to the right or going up or down, or that node can also move left or right. So it does really have only 2 degrees of freedom. So 2 degrees of freedom here, 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 and clearly, you can see that in this scenario that yeah, this node can move both ways. This node can move both ways. This node can move both ways, and there's an error here. It's not showing the circles. There's 2 circles here representing a roller, which allows this point to move left or right. And that's why you see a degree of freedom there as well. This node also was supposed to be in rotors, and it's not showing up. But trust me, this can also move left or right if you were to have a roller. So this clearly shows you that there is a degree of freedom here, and that's this one here and this one here, while these other ones can move left or right, and it can move up or down. And that's where you see 2 degrees of freedom per node. While when I was discussing springs, there's only one. So I could discretize, and I'll just do it all at once here. I can idealize each truss. Each of these trusses, I could idealize it. I could idealize it. I could idealize it as a bar. So let's take a single bar, and I'll rotate it just for fun. I'll take that truss and I'll rotate it to have it straight like that, just to be able to study it better. That bar can expand or contract. It can stretch or compress. But that is a local element behavior. I took a single truss and looked at it. And I'll say this node is I, this node is J, and this load is P, and this load is P. And there has to be, by equilibrium, if I apply a load P here, there has to be a load P in the opposite direction that renders this local element in equilibrium. That's the only option. So we know the stress is P over A. We know that. That's a given. The stress is P over A. So if I have a load P, then the stress, the actual stress in this bar with cross-sectional area A is stress equals P over A. We should have learned that in mechanics of materials or strength of materials. And if you have forgotten about these concepts, I invite you to go ahead and look at some of my mechanics of materials and strength of materials YouTube lectures on that topic. We also know that the strain is the change in length of, so that say the original length is L. So then the strain has to be the change in length of this bar divided by the length. Well, guess what? In this case, the change in length is this degree of freedom, this deflection here, dj, minus the degree of freedom here, that deflection di. dj minus di is clearly the change in length divided by L. That gives me the strain. And so we know that the stress is related to strain. And the stress is related to strain through this Hooke's law. Stress equals E times epsilon. And so now I can plug this in. I can plug that in. And when I plug P over A on the left side here, and this equation on the right-hand side here, I get this formula. And I can now solve for P. So when I solve for P, I get EA over L, dj minus di. And I'm going to call this K, the stiffness K. So that's the stiffness of this bar. And I know E, the modulus E of the material. A is the area, the cross-section area. L is the length, the initial length of that element. And so now I also can write this equation in matrix format. If you recall, this force here is Fi and the force here is Fj. If I lived in terms of Fi and Fj, then I get, for the first equation, I get K times di minus 1 times K dj. And that's exactly, that'll give me equal to Fi. That's exactly my first equation here. And the second equation, the same way, I can also show you the second equation. And so that is the element behavior for a bar that's straight. And I took that bar and moved it straight, but that's a local element behavior. But what I'm going to do here is the following, okay? Is that the trusses are bars, are really these bars, okay? We all agree that these are bars. These trusses are like these bars. And that these bars are free to rotate. And so we can use a 1D bar stiffness relationship to then figure out how to deal with bars are not oriented straight. Because this derivation I made here was for a bar that's straight. But I have bars that are angled. So I have to figure out how to deal with that. They're trusses, right? And I'm calling them bars. And so the bars are assembled in different orientations. I have a bar going this way, a bar going that way, a bar going this way, and they have different coordinate systems, right? So I have to figure out how to deal with that. So I'm going to do a little trick, and I hope you can follow this trick. I'm going to take the bar in the local system. In the local system, I have x, small x, and small y. And please follow me along. And I hope everybody here is taking notes as you're listening through this lecture. Because if you're not taking notes, then it's going to be very difficult to have the concepts ingrained into your knowledge base. And it's going to be very difficult for this knowledge to get reinforced so that you can later apply to various concepts that we'll be learning. And so I encourage you, highly encourage you to understand these concepts now by writing it with me. But here I have a bar, and that bar has a local element system XY, local coordinate system XY. And that bar could be oriented and at an angle beta respect to the global x equal x axis. So say the global x axis, this one here, x and y global system. This small x is related to the global x through beta. So this bar is rotated by an angle beta. And I think everybody here will agree that this point in the local system can move to the right and up. So this delta, del jx, and del jy represent the deflections of this node in the local orientation system. So this can move to the right and up along this x and y, right? Along this x and y. The good news is I can take this deflection here, and I can decompose it. I can decompose it for in the x and y global coordinate system. So I've done that right here. So you can see here, I've taken this del jx, and I have written the component that goes in the x direction. And we know that that component is del jx cosine beta using trigonometry. And then this one here is del jx sine of beta. And I know that's the case. And you know that's the case because you can use trigonometry identities to figure it out. So here, I'll just draw it here quick so you can see that. So I'll draw, I have a component. So there's a deflection here. There's a deflection here. And I have a deflection. There's a deflection I'm talking about. And I'm going to decompose it into this one and this one. So if you use trigonometry, you can figure out that this angle is the same angle as that by similar triangles. And so that one is beta. And clearly this deflection can be decomposed to this one, and that's that. And this deflection can be decomposed into that one, which is that one. So I hope you've seen this before from trigonometry, and that's okay if you haven't. I encourage you to kind of derive this yourself. So I've done that one. I've done that one. What about doing this one? Right? So if this is alpha, this beta, this is 90 minus beta. I'm sorry, yeah, this is 90 minus beta, right? And so I can do the same thing. I can decompose that one, and I'm doing it here, by the way, and here. And I'll get del jy cosine beta and del jy sine beta when I decompose that particular deflection that you see there. So again, I'm taking each of these ones, each of these deflections, and decomposing them in the global coordinate system, which is x and y. Okay. And so what you see here now is that what I like to know is when I decompose this del jx and del jy, and I decompose it here as well for the del jy component, what I'd like to know is how that relates to the global coordinate system. In the global coordinate system, I have x and y, and I would like to get it to know how the djx and djy, which are deflections in the global coordinate system, how those relate to del jx and del jy. Well, the way I did that was I decomposed del jx into the x and y, and I decomposed del jy into the x and y directions. And by doing so, now I can figure out how to relate djy into these two components. So let's look at that. djy, which is here at the bottom, is equal to djx, which is this component here, djx sine beta, plus, and then I have this component, djy cosine beta. So obviously djy and djx, del jx and del jy, both contribute to the y direction, and they contribute by this amount plus this amount, okay? And then I have djx. Djx is going to be anything that contributes in the x direction, which is this del jx cosine beta plus del minus, in this case, of del j sine beta. And you can see that written here. So now that I'm able to figure out how to express the local coordinate system to the global coordinate system, I'm ready for the very next step. And that was an excellent question, by the way. I really like that question because it shows that you care about understanding the idealization, right? I think that's an excellent question. And it is the kind of question you want to ask yourself. Can I make this modeling assumption? And yes, I agree with you. This seems like it should carry a moment. But when you look at the scale of things, you could make the conclusion that perhaps this acts more like a pin since it's so small compared to the scale of the rest of the structure. So I do understand that you in my book, I do describe how you could come up with an approach for modeling frames, and frames can actually transfer moment. But I don't think this is the right moment to discuss that. Moment, no pun intended. I was discussing moments, and we're talking about moments. So at this moment in time, we don't want to discuss moment transfer through a joint like that. In my book, chapter 6, we discuss how to do that, but I think it's too premature to get there yet because I am really trying to connect you to the fundamentals of finite elements, and that'll be too quick for me to hit that. But yes, you can model that with frames and beams, and it will be more accurate representation. Very, very, very good question, and I would like to see more of those coming. So now that I came up with a realization that this node, the degrees of freedom of this node in the x and y direction, which is given by these variables, can be expressed so they are related to the local coordinate system. Now what I can do, I can write that in matrix format. And anytime you can write things in matrix format, the better is for us. And the reason that's better for us is because we in finite elements, you really need to learn matrices because it's the way that you systematically solve problems using finite elements. That's why that's so beneficial. And so I'm going to say this. I don't want to confuse you more, but I kind of have to. Do you agree that this was for node I and this for node J? I only did that for node J, right? I only did it for this end. So I only took that end, and I know it moves to the right and up relative to this coordinate system. And I only looked at that one, but I didn't look at node I. Node I also can move up and down, right? And don't lose sight that what we're doing is we're idealizing a bar that's at an angle, and I'm looking at it as if it was straight. But right now, what I'm trying to deal with is how do I deal with that angled truss? I have to deal with that somehow. The good news is that the same derivation I did for node J is the same for node I. It doesn't change. It's the same idea. Just if I just drew everything here, it will look the same. So I know that for node I is the same. And what I'm going to do, I'm going to put everything in column vector. And I'm going to say, okay, well, for node I have dix and diy. For node I, remember that's for node I, the single truss element has two nodes, I and j. So for node I have these two deflections in the global coordinate system, which is more useful for me. And for node j, I have 2 degrees of freedom. That's djx and djy. So I have a total of 4. That makes sense. When I go back here, I can see that. I have 2 degrees of freedom here at this node, right and up, and at node I have right and up. So I have 4 degrees of freedom. That makes total sense to me. 4 degrees of freedom here. Now you will say, well, how did I got to this? This looks crazy. It's not crazy. We'll take this matrix and put it in this corner. Take this matrix and put it in this corner. Let's see if it makes sense. So let's look at these equations here that I derived at the top to see if I get it from looking at this. So let's look at that. djx, if you haven't learned matrix multiplication, we'll learn it quick. djx is equal to 0 times this component plus 0 times this component plus cosine beta times this component, which you can see here, times this minus sine beta times this component, which you can see here. You can see very clearly that I got that equation by using this matrix multiplication. Look at djy. djy, which is the bottom equation, is djy equals 0 times that, 0 times that, plus sine beta times that, which is this component, plus cosine beta times that, which is this component. Clearly that's djy and djx, and I'm able to recover it. Very similarly, I can do it for I, and since I just told you that the equations are the same for I, clearly you can see that it works out. These zeros, what these zeros are doing, they're trying to decouple the behavior at node I and node J. That's all they're trying to do. So I'm going to call this whole thing transformation matrix T. I'm going to call this whole thing transformation matrix T, and I'll call this whole column vector the local deflections in that bar, del. And I'm going to call this the global deflections of these nodes in the global system, d bold here. Okay, so d bold equals the transformation matrix T times the local deflections at the nodes del. Okay, so that's what we've done so far. So continuing on, since there's no questions, I want you to point out something very interesting. If you take the inverse of T bold, you were to look at the inverse of this, I guarantee you that the T inverse will give you T bold transpose. So you get this transposed. And I invite you to take some time to do it yourself so you can see that is the case. Okay, very similar, right? So I demonstrated to you that D bold in the global orientation system, this is deflections in the global orientation system for the two nodes is equal to this transformation matrix. And beta, again, is the angle of that truss relative to x in the global coordinate system. That beta is going to be known for every truss, okay? That matrix is fully known. Times the deflections in the local orientation system to the bar. We can apply that idea to forces too. I think everybody agrees that there's a local force in that element that's oriented this way, and a force perpendicular to that element in the local orientation system, small f. But then the global orientation system, I instead have f bold, f uppercase, and that I can relate in a very similar fashion I did it here for deflections. I think everybody here can agree with me that the same applies for forces. It's no different. It's just I changed the variables from deflections to forces. It's more intuitive. I agree it's more intuitive to look at it with deflections, but it's also intuitive to do it with forces. It's the same idea. So what I've done, I've taken all this D and make it uppercase F to represent forces. And these dels, I've changed that to small f's representing local forces to the element. They're oriented along the element coordinate system. This is T bold, T bold again, and this is small f bold, and this is big F bold. And I'm basically relating the local element forces times the transformation matrix, and that should make it equal to F bold in the global system. So I see this almost like a transfer function. Think this of a transfer function. I know the local values to the element. If I multiply by this transfer function, I'll get it in the global system. That's the way I like to look at it. I like to look at these things as transfer functions. So again, d bold equals t bold times delta, f bold equals t bold times small f bold and del bold here are both vectors that represent the behavior in the local system, while big F bold and D bold are in the global orientation system and represent force and deflection. Very nice, very cool. And remember that T inverse equals T bold T. Remember that. We're going to use that very soon. So, do you agree then that I can invert T like that? And I get del equals T inverse D. But this is T transpose. So that's what I get there. So I can invert it. If you're okay with that, that's what I just did. Do you also agree that I can do this for F bold? So I can invert F bold, this vector F, and I should put this like that. In my book, I use these squiggle lines for vectors and a straight line for matrix. So I'll just keep that convention for now when I write it down on this whiteboard. I want to solve for F, so I have to do an inverse again. So T, that's a matrix, inverse F bold or vector format. And this again is T transpose. And so that's what you see there. That's what you see here. So I'm able to solve for D bold and solve for F bold. Okay. And the reasons for doing that will become apparent soon. Why I'm doing these inversions. So let me look at the local. So I have that. Just trust me on this so far. But now let's look at the local element behavior in the local element system behavior. Remember, small f and small del are in the local element system. Okay. So what does that look like? Well, I already know. That for a bar that looks like this, with a local element system small x small y, that in reality the only forces this thing can transmit is axial. So I have Fix at this node, Fjx at this node, and I know that they're related to the stiffness matrix k minus k times del Ix and del Jx. That is the element formulation for a bar in the local orientation system. And I derived that earlier in the previous lecture for springs, but I also kind of derived it really quickly here, as you see here. For a straight bar, that's what I have in the local element system. In a local element system does not know how it's oriented, so who cares? I could have drawn this straight and it will not matter, right? I could have drawn this straight and it will not matter because I'm looking at the local element behavior. And that's what I got. I got it for the springs. I got it for a bar. And that equation is true for everything. But what I can do a little trick. I'm going to do a little trick. I'm going to go ahead and expand this matrix. I'm going to expand this matrix by adding rows of zeros and columns of zeros. 2 rows of zeros and 2 columns of zeros with a little trick in mind. This right here, Fix and Fjx are the ones you see here. And del Ix is right there and del Jx is there. We know one thing for a fact, that this force here acting in this direction is 0. We know that there shouldn't be any forces going that way in the local coordinate system. We know that. So as a consequence, since that's 0, you must have 0 row and 0 here and 0 row and 0 here. I can demonstrate for you that these equations are recovered. So let's see, Fix is equal to k times del Ix minus k times del Jx. Let's look here. Fix is equal to k times del Ix minus k times del Jx. I got the same answer. Let's look at the second equation. Fy is 0 times that, 0 times that, 0 times that, 0 times that. That's 0. Exactly. Fyy, you shouldn't have any load going that way because bars can only take loads axially, locally. let's look at fjx. Fjx is minus k times that, plus 0 times that, plus k times that, plus 0 times that. Well, that's exactly what I got here too. So this here is equivalent to that. Everybody can agree with that, with me. And I've ordered it in a very smart way. I ordered it so I have the node I and node j next. So I have ix and iy, which is these ones here. And then I have ijx and jy to be like that. And I'm doing it to be consistent to what I had previously done when I expanded these matrices. And what I noticed very quickly is that this here is del, like I had before, and this is f, like I had before. And this I want to call the local element stiffness matrix, K prime. Okay, that's for element E. This is true. For every single element, this is true. For every single element. What if I do a little trick now? We already know that F bold equals T bolts times F. We know that. And we know that from here. It's all about tricks. Finite is all about tricks. Systematic ways of doing things quick and smart. Then I have del equals T bold T D. Okay? That's what we got. And we got that from inverting earlier. I showed you how to do, so I showed you this and inverted T bold to the other side, and T bold inverse is T transpose. That's what we got. Well, let's keep seeing what I'm doing here. But I have this equation also. So I want to find a way of relating them. Let's see how to do that. So let's see, F equals T bold. And then the small f bold, isn't small f bold equal to K prime at the element level times del? Isn't that the case? That f bold is that? But in addition to that, this del is this. So I can plug that in here. And so I get that. I get f bold equals T bold, K prime in the local element system, these springs values, times del, and del is that, so I get this equation. I know T bold for every element. I know what it is. If I know beta, I know this transfer function. I know K prime. I know what EA over L is for every single element. So I know that. I can multiply this in MATLAB or Mathematica. I don't care. It can be done. So now I have a way of relating the global forces in the global coordinate system to the global deflections in the global coordinate system. I have a way of doing that now with this formula. So I'm going to call this whole thing K bold. And let's examine what this looks like for our case. So we know that T bold is this. T bold transpose is this. Transpose is just make this here, just transpose it. That's what we get. And we know K bold is this. So if I multiply this whole thing out, I get the element stiffness matrix for a truss in the global coordinate system. When you see C here, that's cosine. And when you see S, that's sine. So that's cosine squared beta, sine, cosine, and so forth. And you can see here K is the stiffness of that single truss element, which is EA over L. We already covered that. We discussed where that comes from. So let's look at the element formulation. I have 2 degrees of freedom here, 2 of them here, and they are in the global coordinate system, which is great if I want to assemble different trusses with different oriented at different angles. That's why we did this. We did this because we want to be able to assemble things together, and every truss can be in different coordinate system. But we found a common global coordinate system that can be used for every single truss and allows us to bring everything together nicely. So this is what we get for the element stiffness matrix. The new code numbers are this. So for node number node I, that's just a label. I is just a label. Don't get confused. You see so many layers, you go crazy. No, no, no. I is just a label. X and Y tell you the direction that we're talking about. So for node I have two directions that that node can move, to the right or up. So that's the first two, 1 and 2. And then the next node is J, and you can see here you can move right or up, and that's what you see there, that I have this DJX and DJY. So I have four degrees of freedom, 4 degrees of freedom. Okay. Um, so these are the new code numbers now. Like when I was looking at a single spring, it only had 2 degrees of freedom because this every node can only move axially. But now because a node can move to the right and up, I have 4 degrees of freedom system. And I'm numbering them so there's 1, 2, 3, and 4. That numbering is important because that's the way these ordered here, 1, 2, 3, 4. The reasons for numbering in that particular matter will become important later. Okay. So we made great progress. We discretized the body. I showed you how to discretize it. We developed the element local behavior. We figured out how to come up with the element local behavior. And we came up with a sorry, not spring, but we came up with a force deflection relationship for a single element in the global orientation system. And then what I can do next is to put code numbers here that can then be used to assemble the system together for use and to solve it. And this is very, very powerful. Let's look at this particular example. Yeah, so let's look at this example. Um, in this example, and I'll walk you through it. I think everybody can agree that can label the nodes. So say I have this truss system. I have this truss system, there's clearly 3 trusses here. Is fixed on one here. So it's fixed here and it's pinned here. So it's pinned here, but it can roll here, right? So let's look at that, right? And I can label the element numbers whatever way I want. I can make this 10, 11, 12. I made a 1, 2, and 3 for the trusses. And for the nodes, I can also number the nodes anywhere I want, but I number them 1, 2, and 3. So now what I want to do is to use a code number. But before I do that, I need to label the degrees of freedom in the global orientation system. This node is fixed, so therefore that's 0 and 0 because it's fixed. This node 2 is next. Well, that node, I'm going to make it 1 and 2. And this node here is only allowed to move up. So that's 0 and that's 3, right? So let's look at that. Node element number 1, I'll have to draw element number 1. Element number 1 here has a beta of 0, and I have I and j here, so I have to start counting there. So for element number 1, I have 0, 0, 1, and 2 because element number 1 is connecting this node to that node. So that's why you see here 0, 0, 1, and 2. Now I want to examine carefully. Oh, I erased that. I shouldn't have. I want to examine element 2. Element 2 connects I and j. And if I look at beta, that beta is minus 45 degrees, right? Because I'm defining this beta about the I node and the x-axis. And that's clearly minus 45 degrees. So when I look at that one, I will notice here that it's connecting this node to this node. So that's what? 0 first, 3 next, and then 1 and 2 following. You can see that there. It's matching. Perfect. We got that. We got that one down. Let's look at element number 3.
Professor,
Element
I have
number
a question.
So hold on. So I want to repeat one more time how to deal with element number 2. So element number 2, I have it I and J here. That's the way I drew it. If you recall, the element was derived so that the angle beta is defined relative to the x-axis and about the I vertex, and that was beta. Here, obviously, beta is 45, if I were to use that convention that we had derived earlier. So as a consequence, I have to be very, very consistent. So I goes here and J goes here. Now, when I look at node I, that's element number 2. Element number 2 is connecting nodes 3 and 2. So I have to follow that same code number approach. So for node 3, I have degrees of freedom 0 and 3. For node J, I have degrees of freedom 1 and 2. So I have to write it in that order: 0, and then 3, and then 1, and then 2. That's the way that you have to do it. It has to be done in that order. So for element number 3, that angle is beta, and it's 90 degrees. And it goes from bottom to up. So it's connecting nodes 1 and 3. Node 1 has 0, 0 for degrees of freedom, and node 3 has 0 and 3. So that's why you see 0, 0, and 0 and 3. Okay? The left side here is for node I, and the right hand side is for node J. I want to do something a little bit different this time, not to confuse you, but I want to do it to kind of show you what you will get if I have made element number 2, because I can do it that way if I wanted to. Element number 2, I'm going to make this I and this J, because you can select how you want it. You just need to be consistent. So that has to be defined with respect to X. So this beta now is 135. And now, if I were to write the code number for element 2, is a little bit different. It starts at the bottom here, node 2 to node 3. So the code number now is 1, 2, 0, and 3 in that order. So 1, 2, 0, and 3. That's the order I need if I were to have. You can do whatever you want. You can, but you need to be consistent. Whatever you do, need to be consistent. Otherwise, things will be incorrect. Okay. And so that's the message I have for you, is to keep in mind the how the element was formulated. When I cover triangles and quadrilaterals, we have 4 vertices, it becomes more complicated, and you have to keep in mind how to deal with that. Now that I have the element and the code number, I'm primed, because I know for element 2, for every single one of these elements, you have to calculate k, and that k is going to vary because beta is going to vary, but the k and the L can vary. The length of every truss can be different. So the modulus can be different too, and the cross-sectional area can be different. So you have to be careful. The k can be very different for every element, but for element 2 is this: 45 degrees. The modulus is a, and the cross-sectional area is a. So now that we have that, we can assemble. How we do that? For element 1, I have these code numbers that I can write down. And you can see that the code numbers are given here. For element 2, I have these guys that came from here. For element 3, I have these code numbers that come from here. And now, how many degrees of freedom I really have? I have 3, because this can move, this node can move to the right, this move can move up, this node can move up. I only have 3 degrees of freedom. So the global stiffness matrix can only be a 3 by 3. So I have 1, 2, and 3, 1, 2, and 3. And I will now search. I'll do a search. And that's how you'll code it up. You have to do a search looking for that. So I look here for position 1 and 1, which is this one right here. I'll look and try to see where I see it. I see a 1 and 1 here. I see a 1 and 1. I see a 1 and 1 right here. And you can see that I don't see any 1 and 1 in now element 3, so those two get added. And then you can fill this up. Just fill it up by doing that search, the way I just explained it for that one position. In case you're confused, I'll do one more. So let's search for this position, 3 and 1. I look through everything. I'll look through everything here. I'll clean this up to make it clear. So 3 and 1. So let me look. 3 and 1. Where does it show up? I only see 3 and 1 here. And that's what you see I wrote there. So you just do a search and find out where it shows up. Now, let's look at the load. The load is interesting. The load, do I have any load applied on this degree of freedom? No. Do I have any load applied going up and going to the right? Yes. Is P naught cosine 45 and P naught sine 45. So that's what you see there. That's the load applied at that, and you can see we have it written here. Okay. And if you're confused how to get to that state, just look at degrees of freedom, 1, 2, and 3. You can number it 1, 2, and 3 and figure out what loads are applied to those degrees of freedom. And in our case, is very simple. Now that I have the stiffness matrix and force vector, I'm primed. I'm primed because remember that F equals K times D. And I'll use the convention in my book with the under script. I can solve for the deflections D by inverting the stiffness matrix and multiplying by the force, which is a vector. These are vectors according to my book. So I can calculate deflections. And once I know deflections, I'm ready to go. I'm ready to go, and I have been successful. Very, very nice. Very powerful. Very, very powerful. And it's very, very exciting. Okay, so I'll continue then. Let's take another example. Example number 2. I have a truss system, and this truss system has, we have about 6 trusses, a load 9 applied here, kips, 6,000 pounds applied here, pinned. And the aluminum truss system has going to be interesting because every truss is going to have different area, and the length could be slightly different from each other. So we want to account for that. So what is the first step in the whole process? The first step is to number your elements. Just number them. I don't care. You can make it 10, 15, whatever. I did it consecutively. 1, 2, 3, 4, 5, 6. And I see here there's pinned and pinned. So that node is 0, 0, the degree of freedom. Here, 0 and 0 because it's pinned, so it cannot move. And then here, I have the following. I have for this node, I have 1. So that's node number 1. Then I have this as node number 2, and this as node number 3. In node number 1, this can move right and up. Node number 3, this can move right and up. And this node can move right and up. And so with that said, I can now create my code number. So element number 1 is 0012. That makes sense. 0012. For member number 2, which is right here, is going from bottom up. Notice how I put the arrows here. I put some arrows here. With that, I can now write my code numbers 1200. You can see that here, 1200. Member number 3. Member number 3 is right here, and it goes from left to right. I draw an arrow, and that's going to be very useful later when I calculate my betas. 0034, bam. Element number 4 is this right here. 1234, 1234. Element number 5 starts here. 1256. And then element number 6 goes from top to bottom. You can see it's diagonal here, but I made an arrow there. So I want to follow that same way. So 3, 4, 5, 6. And I have to have the code number to be consistent. Remember, we numbered it I and then J. So node I and node J, and within node I have 2 degrees of freedom in the X and Y direction, and then for the J in the X and Y direction. So it needs to be in that order. And that's why I'm trying to emphasize the importance of that. So um, the truss structure has been divided into 6 two-node truss members. The positive sense of the local x-axis is arbitrarily chosen for each member, and this information is then determined with code numbers written for each element. Very, very nice. So let's look at the solution to this example. Member number 1 is this one. I drew the arrow from left to right, which means that the beta is respect to the node on the left, and obviously that makes a 0-degree angle with the x-axis. So beta is 0. I know the modulus E for this material. I know the cross-sectional area for member 1, which is 5.6 inch squared. And then I know the length. The length is, and you have to be careful of the units. That's why you see a 12 by 12, because this was given in feet. And I'm going to trick you in a lot of the problems we're going to do, because I want you to learn that in real life, people are going to give you information in different units, and you have to be smart about what units to use. So you have to use the right units. And here we have 12 by 12. And I get 388.9 cubes per inch. Okay. Um, and so then I can substitute that here for K, and that's what I get. And I will keep the numbers here, the code numbers, so I can keep track of that. Member number 2, let's look at member number 2. Member number 2 is going at an angle from bottom to up. And yes, that looks confusing, how I calculated a beta, but it's going from bottom to up. And I already told you how that needs to be done. I'm looking at this member here, and I is here, J is here. And so the angle I'm looking at is this one. That's the beta. And you can use trigonometry to find this 143 degrees. Again, the modulus is known, the area is known, the length is known. So I know K. I know the stiffness metric for this one. For member number 4, which is this one right here, again, I is at the bottom, J is at the top. So this is the angle I'm looking at as a right-hand triangle with 90 degrees there. So I just plug it into my formula, and I know the area for that truss, I know the length. I can calculate K. For member number 5, which is this one here, that's obvious. That's beta equals 0. And again, put the code number up here. You created the code number table here, use it. I created it, use it. Member number 6 looks more complicated, but it's not. So that's this one right here. That's I now, and that's J. The angle it makes is this one here, beta, with the x-axis. That's why it's negative 36. You can use trigonometry again to figure it out. E is known. The area for that cross-sectional area is known for that truss. L, the length is known. Therefore, you can calculate K. Now, I'm primed. I'm primed. How many degrees of freedom I have? Let's look. I have 1, 2, 3, 4, 5, and 6. These ones are fixed. Nothing's going on. So my global stiffness metric should be a 6 by 6. I will number it as such: 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And I'll start searching. I'll start searching for 1 and 1. So let's look at where 1 and 1 shows up. 1 and 1 does not show up here. It shows up here. 1 and 1 shows up here. And it shows up here. Shows up 3 times. So I can add it up. You can see that I added up there. I added 3 of the instances there. And I can then do a search for every single one of them and add them up. Now you notice I kept this empty because the stiffness metrics for a conservative system will be symmetric. And this is a linear system. There's no reason to believe that it's not symmetric. So I'm done. I'm done developing the global stiffness matrix. The global structural displacement and load matrix can be looked at now. Let's look at that. So the deflections in the global system is this. What are the loads in the global system? Let's look. I only have 9 kips applied on this one and this node. And the degree of freedom is the vertical one in the negative direction. Here I have drawn it, the degrees of freedom. So let me erase this so it's more clear. I'm only applying a load in this degree of freedom, and I only load in this degree of freedom, but in the opposite direction as they were defined. So that should be negative when I put it there. So therefore, the only ones that have values is this one, -9 and -6 for this one. Everything else is 0. I don't have any loads applied for anything else, just for those. Okay, just for those. Again, degree of freedom 2 and 6. Those are the only places I'm applying a load, and that coincides with what I have here. Now I can solve it. I know K, I know the forces. Invert this matrix, pre-multiply against the vector, and you get the deflections. And that's what I get for the deflections. So a question came up that I think is worth just quickly covering. At that node here, I had a load applied of 6 kips. But if I had a load here of 8 kips, say, in addition, I should make this 8. So that's all we discussed, is that you could have loads applied axially, but also vertically. I already covered that example, but it's just to kind of emphasize. So I know K equals Q. I can invert K inverse to get this, and I can get the deflections that way. But I want to now post-process. What if I want to know the forces? What if I want to know the forces in here, here, here? If I want to do a cut there to figure out the forces. And you guys learn a bunch of methods, mechanics, and materials, but I want to show the beauty of doing it systematically. Because the way you learned it was not systematic. This is going to always work with a code. You can actually write a code every single time and it's going to work. And I can. And let's look at how you will do that. So the equation for the member force in the local coordinate system is this. I already covered that before. The force equals that. This is in the local force system. This is a transformation matrix. That's in the global orientation system. But I know that this equals the stiffness times the deflection. And I know the deflections already. And I know the stiffness matrix local to that element. And I know this transformation. So I can calculate the forces in every single element. Let me show you that. So let's look at that. For element number 1. Element number 1, the for element number 1, the degrees of freedom are 0, 0, D1 and D2. But guess what? I know what D1 and D2 are. I already calculated that here. So I know T, because I know beta is 0, so I know T, the transformation T. I know K is always this. And so I know D. So if I multiply everything together, I get the forces in that truss. What's amazing, you can see here that I get 28, and I don't get anything vertical. That was the assumption, that a bar element is not going to have a force going that way. That force does not exist. It's only going to be acting axially. You can see that our assumptions are working out, and these calculations are working out. It worked out. Beautiful. Beautiful. It worked out. And it's very, very cool to see. Let's look at the next one. And remember, this K here is this K here. in case you forgot, I want to show what K that's it. That K that we're talking about is this K. Don't forget that. Let's look at the forces in element number 2. Element number 2 is actually diagonal, is at an angle. So that'll be interesting. I drew the arrow, so you should remember that this is the 1 degree of freedom system, 2, 0, and 0. And you can see that there. I labeled it correctly. I know D1 and D2 and 0, and I know these deflections from my calculations. I know this stiffness matrix, this stiffness matrix, because I know beta for that. It was 143 right here. I know the transformation matrix for this element. I multiply everything together and I get the force. And check that out. Check that out. The forces the forces are axial, right? Local to the element. Check that out. I know exactly what's going on here. I know the force in that element. And I know what is going on with that force, which is very, very powerful. Very neat. I think it's very neat. And I know the member is in tension. I also know the member is in tension, which is also very amazing. Element number three, and you may ask me, oh, why is the element in tension? How you know that? Okay, let me show you so you can see how amazing this is. I'll take this truss element and draw it here. This node I, this node J. This minus 25, that means the force needs to go away from the node. And that's J. That's always, so the convention is this for positive. So if it's negative, that means it goes away from the node for node I. But if it's positive for node J, it's correct. That's the convention I have. And you can see that it's pulling that truss apart. And that is correct. Okay. Very, very powerful method. That's systematic. I don't need to do more mechanics of materials. I just run a finite code with these trusses and I can get, well, I don't want to preach not to do it by hand. I think it's a great idea to do things by hand. But you have a systematic approach of doing it now. Element number 3, look at this element number 3. Same thing. 0, 0, the code numbers for that. 3 and 4, that's that. I know these values. So I know this. Beta is 0. I know this. I know the transformation for this, which makes sense as the diagonals are 1. Makes sense because that means that the bar is completely horizontal, which is the way I derived the element in the first place. And I get the forces for the element. I get minus 8 and 8, and it's also in tension. When I look at the physics, you always want to look at the physics. Do the physics make sense? The physics makes total sense. If I apply a load in this direction, you expect this bar to be pulled in tension. That makes total sense. You want to think about that from those terms because you want to make sure that things do make sense. For element number 4, that one is a little bit tricky to know if it's tension or compression, but I think you can see that if I apply a load this way, I'm going to compress this bar. To me, it seems like I should be compressing it. I also know which way I created the convention for this. I have an arrow here which says that this is I, this is J. So they have 1, 2, 3, and 4. 1, 2, 3, and 4. And the angle is 90 degrees against the x-axis. So again, I know all these values. I know K because I know that. And then I know the stiffness matrix for that element. And I know the transformation for that. So I get 6 kips. Again, beautiful. And it's in compression. Makes total sense. How do I know it's in compression? This actually is a good one to do really quick. Let's look at it. Is 6 for FIX. So that means this arrow is pointed correctly. This is minus 6. But in my convention, you can see here, I drew it that way. Minus 6, that means it goes in the opposite way. So that means the member is in compression. And I don't want to keep boring you, but then we have element F5, and the same applies. I'll just do 6 just for fun. If I apply a load here, I expect this to be in tension. And this is I, and that's J, because I drew the arrow that way. So then I have 3, 4, 5, and 6. And I know that vector, I know the deflections. I already know what that is. And that's going to be this column vector. I know beta, I know K, I know this transformation, I know this force. This K you already know. You don't have to keep calculating K again. We already did that in the previous step when I was doing this case. So let's look at member 6. Where was that? Here. I already did this calculation. You don't have to repeat that calculation. That calculation is already done. You can just borrow it again for this other calculation I'm doing here. So in reality, the only thing, you basically calculate everything already. All you have to do is multiply it differently. And you can do this quickly in Mathematica, MATLAB. My book shows you how to do things in MATLAB, how to code it up. Reaction forces. What if I want to know what these reaction forces are? What if I want to know that? That's a little bit more tricky because I have not discussed that yet. If I want to know, because of course, do you agree? Do you agree? Does everybody agree that when I apply these loads, since it's pinned here and has a roller here, actually it's pinned on both ends. Yeah, it's pinned on both ends. Do you agree that when I apply a load of 9 kips and 6 kips, it's going to create a reaction force here? I want to be able to find that reaction force. So the way to do that is going to take a little more work, but you want to do it. You want to now, you have this degrees of freedom 1, 2, 3, 4, 5, 6. You can do now the ones that were 0, just make it 7 and 8, 9 and 10. Just add those degrees of freedom. Now assemble the full stiffness matrix as if there is no constraint to them. So for example, the code number for element 3 here, for element 3, the code number is 9, 10, 3, and 4. Reassemble the whole system again, but assuming that everything can move, So for example, element number 1, the code number for that is 7, 8, 1, and 2. Assemble everything, all the stiffness matrices, assemble them as if there's no constraint. It's a little trick. Now you know that these deflections are 0. We know that. You know that because these are fixed. So just make them 0. You know these deflections from the previous step. You know all these deflections. So that is fully known. The fully assembled stiffness matrix is going to be 10 by 10 because I'm going to assemble the whole thing, like if these were all there. So when I multiply that stiffness matrix by this column vector, I will not only recover the forces I applied, which are these ones, but I'll also get the reaction forces. That's beautiful. That's insane and beautiful at the same time, both beautiful and insane. You can check that you get the forces that you applied, but you can also get the reaction forces. Okay. Okay, so how will you do this in Abaqus? I ran the same problem. The same problem you see here, I ran it in Abaqus. And you can see here that I have how many nodes? I have 1, 2, 3, 4, and 5. So the first step, anytime you see 2 stars asterisk, that means commentary. So the first line here is getting ignored. And in the first step here, we want to define the nodes. So star node, you're going to define the node number 1, 2, 3, 4, 5. That can be arbitrary. You can make it up. For node number 1, I made it 0, 0. And you can see that there. I defined it 0, 0 there. You can see that defined there. For the node 2, I have 144,0, and so forth. You can see all the nodes have been fully defined. Notice I'm using inches here. So the code does not know what units you're using. You have to be consistent. So I'm using inches there. But you see all 5 nodes defined. Now the next step is to define the connectivity matrix. Now you can define it whatever way you want, because I'm not doing it by hand anymore. I'm just letting the code do it for me. So I'm selecting the element type. So star element allows you to select the element type. You can see that there. T2D2. That's a 2-noded truss element in 2D space. They also have a 3D element. But we're looking at 2D. So that means 2D. 2D is 2-dimensional. And the last number 2 means 2 nodes. The truss element has 2 nodes. And you can see here very quickly that node number 1, element number 1 is connecting. Element number 1 is connecting nodes 1 and 2. And that's what you see defined there. Element number 2 is connecting nodes 4 and 2. You can do whatever order you want, but that's the order I did it. That's fine. You can make 2 and 4. It doesn't matter. And that's what you do here. You define the connectivity, how things are connected, which is exactly what we're doing by hand. This is your element code number, but we're telling Abaqus about it. Next, I'm going to define the properties of the cross section and the materials that go along with them. So, for example, for element number 1, I give it a name, L set element. You can make it whatever name you want. You can call that L set, you can call it VNA if you want. And multiple elements can be within the L set. It's just a group. You're creating a set of elements. And you can see here that I call it LM1 for whatever reason I called it that day. And I'm saying that the material that you should use is aluminum. I haven't told it what aluminum properties is yet, but I will tell it later. And I told it, if you go to the Abaqus manual and you say, okay, for a solid section for a truss, what should I provide? And what you provide is a cross-sectional area, which is what we provide here, 5.6 inch squared. And if I have multiple elements, that have that cross-sectional area, I will just provide that underneath here. I'll just put it underneath there. I'll have multiple lines under element set 1. So then after that, I provide the material, which is modulus of 10 E6, Poisson ratio 0.33. That's what I'm doing there. In the next step, I'm invoking a static solution. We're not doing dynamic right now. I'm fixing the degrees of freedom here. You can see here node number 1 and 4, completely fixed, 1 through 6. We're fixing degrees of freedom 1 through 6. And we're fixing to 0. And then finally, you're going to love this because it's going to relate to what we've been doing. We applied a concentrator load, C load. Star C load is a concentrator load. And applied it to node 2. You can see that there, node 2, in the degree of freedom 2, which makes sense. That's a vertical. So if that is my degrees of freedom 1 and 2, right? That is a correct one. It's negative 9,000 pounds. And then for degree of freedom 3, again, degree of freedom 2, negative 6,000 pounds. Very nice. That's set up. Now you go to Abaqus, import that. You can write this in Notepad, by the way. Save it as a .imp file, input file. Import it into Abaqus, CAE. You can import an input file, and then you can run it. And when you run it, I have good news for you. The solution I got is exactly what I got using my hand calculations. Look at that, 0.072, 0.072, 0.696, 0.696, 0.288, 0.288, 0.75, 0.75, 0.144, 0.144, 1.926, 1.926. Beautiful. It matches. It matches and it gives you confidence. And that's why in this course, you'll be doing the problem by hand once in a while and replicating that in Abaqus. So you can build confidence that what you're doing is correct. So who is going to grade you? It's not me. It's not my TA. It's not my grader. It's you yourself, because if you don't match your own answer, then you're doing something wrong and you should fix it. Okay? That's how we're going to go about that. Very good news, though, is that we're going to give you YouTube tutorials on how to do this modeling, and it'll be posted very, very soon for your consideration. So the question has come up that I think is worth discussing is on the star boundary. I have the node number here, and then I have a 0, 0 here. What this means is that if you put 1 and 6 here, what Abaqus does, it fixes degrees of freedoms 1 through 6 to have a value of 0. That's what it's doing. Every node in Abaqus is going to have 6 degrees of freedom. Even if a truss element can only translate and not rotate, every single node is going to have that. And so in this case, because it's pinned, you could also have done it this way. So I could have written node 1, degree of freedom 1 is 0. In the next line, I could have written 1, comma, 2, comma 2 is 0. I could have done that. And that will make this pinned. I could have also written as 1, comma, degrees of freedom 1 through 2 is 0. I could have done that too. And these two are equivalent. Okay? So that just tells you, it just saves you time. Here, you can always open the Abaqus manual. Always open the Abaqus manual. And if you look at the Abaqus manual, and you look at the keyword manual, it will tell you exactly what to put in there. And it's very helpful. Now let's look at an example that's a lot more complicated, little more complicated, not a lot more complicated, but a little more complicated. And you have a situation now where you have a slanted surface. If you have a slanted surface, it's a little bit more difficult because all my degrees of freedom were fixed in this direction or this direction. But now I have a situation where the degree of freedom system, the degree of freedom that's fixed is this way, which is a little bit different. And so we have to think a little bit differently. The strategy then is to figure out how to transform. We have to transform this node so that the global orientation system that I had before, X and Y, now is along this boundary. We have to figure out a way of doing that. Because that way we can then apply the boundary conditions more successfully. You can't really apply a boundary condition in any other way, right? Because it's slanted surface. This point cannot move up. It can only translate, right? So we have to somehow impose a boundary condition. It's not straightforward, but we have to do a transformation to figure that out. The cut numbers that are of concern are 5 and 6, and I'm highlighting them here in bold because that's the only one that has that slanted boundary condition. That's the only one that has a slanted boundary condition. So that's the ones I have to focus on. And so even though there's a constraint at degrees of freedom 5 and 6, we cannot just eliminate them. It's not as simple, right? Because it's slanted. And this point, when it moves this way, is actually moving up and right. So it's not straightforward, put it that way. And we have to think differently. So for that degree of freedom system, I'm going to do a little trick. And I do need your patience to understand it. I'm going to go ahead and use a coordinate transformation. So in the global system 5, 6, I have 5 and 6 in the global system. I want to transform that in the prime system using this transformation matrix. I know that it's slanted at an angle alpha. And so what I want to do is take the deflections in the global coordinate system, convert them in the local skewed coordinate system. And not only that, I'm going to call this matrix TA, the one there. And then I want to do the same thing for the force. I want to do the same thing for the force there. Okay. So we're going to do that. And that's going to help us a lot in this process. Now, I'm going to go ahead, and this is going to look confusing, but it's not. Um, it, it looks confusing, but it's not. Remember that we had assembled a system before, and it looked like this. But I need to really somehow change D5 and D6 in a different way. And so what I'm going to do a little trick. I'm going to transform the displacement field, okay? And I'm going to multiply, the global displacement field will be multiplied by a bunch of ones, diagonal ones, which the area, the section that has to do with D5 and D6. And that way I'm imposing this transformation. Okay. I want to impose that transformation, but I want to do it in a big matrix. And so that's why you see me multiplying this big matrix times this, because I want to get this like that. I want to transform these guys into the local skewed uh, um, roller that it has. And so to do that, that's why I'm doing this multiplication. And notice that if I multiply this first row times this column, I get D1. So I'm not changing anything for the first four. I'm only changing for 5 prime and 6 prime. Those are the only ones I'm changing. Okay, so I mean, now I can do the same thing for the force. And this is my same vector I'm going to use, this matrix I'm going to use. And I'm going to do a little trick. I know D prime is this, Q prime is this. That came from here, right? That came from here. Whoa, sorry about that. That came from here, guys. That came from here. So nothing different there. I know KD equals Q from my original system that I had assembled. Notice I didn't impose any boundary conditions yet. I don't know what to do with it. So I didn't put zeros. I didn't eliminate these boundary conditions because I don't know what to do with a skewed rotor, right? That's moving this way. So I left them there, right? Um, so I know KD equals Q from the original equation. I know D is this because I can invert D by moving that way. So I get D equals inverse D prime. But I know that this is the transpose. So that's what you see there. And I know that Q can also be transformed. Okay. And I know Q. So what is Q? Q is right. So here's a trick. I know what was done. I pre-multiply by this symbol. That's what I did here. Because I know that this is Q prime. You can see that there. So now I have written everything so that these degrees of freedom have been transformed to the skewed degrees of freedom, which is very, very cool because I know this, I know this, I know this, right? And I know this. So I have everything now in what coordinate system I need. And so now that I transformed it, these two here is these two here, and that's the only one that's at an angle. Everything else is XY, in the global XY, right? Those are the only ones that are skewed. The only ones that are skewed are those. So now I can impose the boundary conditions. Now I can, because now I have a rotor here, and obviously it cannot move in the in the D6 prime direction. So that's 0, right? But it can move in the 5 direction, 5 prime direction. So that's what I get. In the 5 direction, it can move. There's no force applied, so that's 0. And now I can solve the equations. Now that I did this, okay? So the nodal transformation is of extreme importance for this to tackle boundary conditions that are skewed. Now let's look at how you will do it in Abaqus. In Abaqus, what you need to do is you need to take that single node 3, that node 3, and you have to transform it. You have to tell just this. Abaqus is going to do the same thing we're doing, by the way. So you tell it how to transform it, and you have to provide the coordinates, the axis. You have to provide the axis x and y. So it's a vector. You're going to provide the vector for x prime and the vector for y prime relative to the x and y global coordinate system. It's unit vector. So you have to provide a unit vector. You can see here that's a vector number 1, and that's vector number 2. A vector always has 3 components, I, j, and k. And so that's how you will do that. And the rest is the same. Nothing changes. Everything else is the same. The only thing you will see here that's a little bit different is that we provided is a different problem, right? We're not applying 6,000 pounds anymore on this node. We instead substituted that with a roller, and that one, then you put a degree of freedom here of 0. You put that degree of freedom is 0. You can see that there. It cannot move that way, right? So you're telling for degree of freedom 2, which in the local orientation system for that node, that makes sense. It's 0, no deflection in that node. Now, one thing I want to point out is notice how, I don't know if you can see, Abaqus even put it at an angle, the boundary condition. Compared to the nodes 1 and 4, you can see them, they're straight. It shows you how it looks to kind of, so you don't get confused. And I guarantee you'll get the same answer. Now, you'll see in the homework and in future projects, in this particular scenario, this is symmetry. Obviously, this is a symmetric problem. This truss system is symmetric. So to tackle symmetric problems, what you will do is you will cut the system in half and model just half of it. It's more computationally efficient. And this comes up a lot. Symmetry, taking advantage of symmetry is very important. Notice how that truss here has cross-sectional area A, but because we divided the whole system in half, the cross-section area for this truss now becomes A over 2, and this node cannot move left and right, so we put a roller instead. That makes total sense because it's symmetric, and I expect this mid-symmetry to stay symmetric, and that mid-plane should not move left and right because it's symmetric. So that's how you'll approach a problem given to you that looks like this. Okay, a question came up. This is actually a good question. What is if I had a roller here? It was fixed here, a roller there, a roller here. Is overly constrained? Not quite. You can actually solve it. You can actually solve it. So in mechanics and materials, they taught you some techniques. You remove the boundary, then you assume that the boundary moves, and you impose a reaction force equal to something. So yes, this will always give you an answer. You can constrain as much as you want, but you always get a good answer. You can always have situations where it's overly constrained and Abaqus will not solve it, but for the problems that I'm discussing today, it should be very, very doable, and you should be able to get an answer. So there's a special case for 3D theory. If you have a truss in 3D space, you can use the direction cosines to define that deflection. So if I wanted to write delta, this deflection delta here, I can write that in terms of the direction cosines, and the direction cosines can be used to put it in terms of the global coordinate system. You can see that I've done that here successfully for del ix for that. I should have said j. Well, I did I, but you get it. For del jx, it's the same equation, right? And the cosine of theta x is simply can be found simply as xj minus xi divided by the length. That gives you the direction cosines for that truss. You can also calculate for cosine theta y and cosine theta z. That will give you the direction cosines that you need, and these values are known. You fully know these things because you know the geometry of the truss, the configuration of the truss. So you can now take that and plug it in here. But I can write this in a compact manner, and I already told you that it's beneficial to write everything compact manner. Um, the first equation can be written like that. The second equation can be written like that. But the idea is that you can write things in compact manner. That's for the x direction. This is only for the x direction. You can take del I x and del j x and decompose it in the global orientation system, the deflections, using the direction cosines, and it can be written in this compact manner. Okay. I can do that same thing for the force. I can do the same thing for the force. The force can also be decomposed. Um, the small f in the local orientation system can be defined in the global force or and the cosine theta x, cosine theta y, and cosine theta z are the direction cosines. And again, I'm going to call this T bold, this transformation matrix T bold. This is small f, and this big F. Now, 3D truss theory can be easily extended from 2D truss theory. We already showed you that for a bar in the local orientation system, this is what you get. We're going to use these formulas. And we know F is T times F. And then we know del is T times D, and that's what you see there. We invert T or pre-multiply by T inverse, and then you get this equation. And when you do that, T transpose is this, K is this, T bold is this. This is beautiful. You get this matrix here. Makes sense. You should have 3 degrees of freedom per node. You can see that here, 3 degrees of freedom here, 3 degrees of freedom here. I get a 6 by 6. So I have 6 degrees of freedom per element, and it works out very nicely. That's for 3D trusses. Very nicely done. We're able to succeed. Okay, we're able to succeed and put everything together in a way that makes sense. And so I do want to point out that 3D elements in Abaqus are going to be T3D2. 3D elements, 2 nodes. And again, all we've done is a little trick, okay? Little trick. We took that force that's aligned with the element. That force is aligned, this force is aligned with the element because that's the only force that can act in a truss. And we decompose that into the global forces using the direction cosines of that force. I know how that force is oriented because it's along the bar, and you know how the bar is oriented. So you can then calculate these direction cosines. You can do the same thing for the deflections. We wrote these equations in a smart way. I invite you to kind of pause and do it yourself. I want you to multiply this row times this column vector so you can see that I recover this exact same thing. You'll see it works out beautifully for node I and for node J. And then I just use the equations that I had derived earlier. These equations here is for local element. And all I've done is gone through the process to get the global forces in terms of global deflections so that I can then use it for to be able to assemble trusses that are in different orientations. But this is what we got, and it's beautifully done. I do want to again point out the physical significance of the stiffness matrix. Take rho I, degree of freedom I. When I multiply the first row times the column vector, I get this equation here. If I apply a unit deflection at degree of freedom J, and all other 0, then I get Kij. And notice that Fi equals Kij in this example. If you apply a unit deflection at degree of freedom J and all other 0, the degree of freedom I, the force in degree of freedom I, is going to be equal to the stiffness that corresponds at the location Kij. So Kij is really the force. So it's actually a very interesting concept. The stiffness at location Ij, right? At degree of freedom I, okay? Kij is really the force at degree of freedom I due to a unit deflection at degree of freedom J, while keeping all other degree of freedoms fixed. Very powerful idea that can allow you to derive the stiffness metrics using some very unconventional approaches. But that's the physical significance of the stiffness metrics. I thank you for listening to this lecture. And again, um, in the book, we're in chapter 6, and here you're going to see the similar discussion, but we expanded with some more examples on how to deal with that. And I invite you to do some of these examples. I think it's going to help you understand this concept more. In chapter 3, we show you how to put a code together if you wanted to try it. If you tried it, it will be provided as extra credit. It is a lot of work, but if you do it, you're going to feel very, very accomplished in doing so and have learned a lot. So, with that said, thank you very much.